So this is from the supplement note on the Brownian motion. I just want to read kind of this different perspective and relate it to what we've been doing. So you see here the definition of what is called the standard Brownian motion, and the standard Brownian motion doesn't differ too much from the process W that we've been discussing. But let me just read this definition, and then we'll relate it back to W. So standard Brownian motion is the unique process BT with continuous paths. W certainly had those as well, starting at 0, and W started at 0 as well, satisfying the following two properties. So let's see if these two properties hold, maybe with some modification for W. So the first one says that the increments of B are stationary and independent. We'll come back to this in a second. And the second one says that each increment is normal mean 0 with variance t minus s. So if you take s equal to 0 in this last part and apply the fact that b of 0 is equal to 0, we see that b of t is normally distributed with mean 0 and variance t, which is exactly what I've written here. This is the probability density of a normal random variable with variance t, and so if integrating it up to the level y gives us the cumulative distribution function at y. And so how does this relate to W? Well, W, and I'm now switching to writing the t from being in parentheses, now just writing it as a subscript, but it's the same W. All I've done there is multiplied B, which is a standard Brownian motion, by our number sigma. Sigma was the limit of delta x over the square root of t. And when you have any normal random variable, which is what bt is, it's a normal mean 0 with variance t, and you multiply it by some number sigma, what's the distribution of that? Well, you just pick up sigma squared in the variance there, and that's exactly what we've seen. This distribution, right, this density here, corresponds to a normal random variable with variance sigma squared t. So that's basically the only difference. When someone mentions standard Brownian motion, you want to think of that factor sigma as being 1. In finance, sigma is volatility. In physics, sigma is related to kind of the properties of the matter in which the Brownian particle is suspended. There's not really any time to go into that, but that's basically the only difference between the W that we've seen. And we see here that it says that one of the properties that the Brownian motion must have is that its increments are, say, independent. Let's look at that first before we look at the stationarity. Then clearly, if B has independent increments, then W should. But now let's try to see, why would our process W have independent increments to begin with? So first of all, what does it mean for it to have independent increments? Well, you look at times, say increasing times, U, V, S, T. These are increasing. They're pictured here, in increasing order, U, V, S, T. And here are the two increments, the increment of W between times S and T, and then the increment of W between U and V. So why would they be independent? Well, the answer really comes from sort of how we designed our W to begin with. W was the limit of this scaled interpolated random walk, W delta. W delta was a sum of a bunch of independent increments of its own, these xj's. These were IID random variables, that took values in the set plus or minus 1. So now, if we just kind of look at the increments of, let's consider the increments of W delta, right? This is what this plot is showing. Clearly this is not the Brownian motion yet. This is, the delta x and the delta t here seem to be, pretty large. And then once they go to 0, it clearly approaches Wt. That's what we've discovered. Now, why would the increments of W be independent? Well, if you just look at it, what's contained between these two numbers? Well, what's contained between these two numbers is a sum of these xj's from an index ranging from, oh, this is a mistake here, this should be 1. Okay, so what would be, if we were trying to describe what goes into this increment of W delta, so W delta from time U to time V, well, the increment would in fact be summing from u over delta t integer part up to v over delta t integer part. So it would contain a bunch of these independent xij's in it, and those xij's would be very different or independent again from the increments that are in here. So what are the increments that are in here? It would be the xj's running from j equal to s divided by delta t up to t divided by delta t. So the xj's that form this increment and the xj's that form this increment are clearly independent. And you want to be a little bit careful here, because when, say, v is equal to s, you may get a little bit of a dependency. But in the limit, and this is something, if you're interested, you could try to work out for yourself, for any sort of uv that are, say, v less than s, you will always be able to take a delta t and delta x sufficiently small to recover the independence property. And then in the limit, it transfers sort of intact over to, our Brownian motion W, Brownian motion with volatility sigma. So, that's kind of, that's where our independent increments property comes from. And so how is it used? Well, this is kind of a standard example of showing how to use independent increments property. This computation here, the expected value of WT, WS, is asking for the covariance function. So that's a common kind of topic in stochastic processes and various applications, to look at how your process, what kind of correlation does it show over time. If you're working with time series data or anything else, this covariance becomes important in application. So here, if we want to compute it for the Brownian motion, how do we attack this problem? Well, this is how independent increments comes in. What you want to do, and this is a standard trick, you take WT, and here I've assumed S is less than T. I subtract and add an S, and the reason for doing this is to form this increment. Now when you multiply WS through, you can write this previous expectation as the sum of two expectations. One of them is WS squared, that's this term, it comes from WS multiplying itself in this side of the parenthesis. And this first term just comes from the fact that WS now multiplies the increment from S to T, and W0 is 0. I just wrote it this way so that it actually looks like a legitimate increment. And this increment is now independent of this increment, and therefore, it's the product of the two expectations. What's the expected value of the Brownian motion, say, WS? Well, it's 0. That's its mean. And so, I can cross out this expectation completely, and this is just asking for what's the variance. Second moment of the Brownian motion is the variance, because the mean is 0. And so what's the variance? Well, we know what that is. It's sigma squared s, which is what's right there. But there it's a time t. Here it's a time s. The next question, but property concerned stationarity of the increments. So that's again property 1. The increments are stationary and independent, and we're now going to look at the stationary part of this. So this you can think about as an increment process. What is it doing? It's, as t is moving, it's looking at an increment between some leading time t plus h and t. So it's always looking at a time and an elapsed time of size h, whatever h is. H is just some positive number here. So just think of h as anything positive. And now you have two time points, t plus h and h, and so this here forms an increment of elapsed time h. And what this is saying is that it's stationary, and this is a little bit similar to our experience with stationary distributions. Something that's stationary doesn't change its distribution as time moves on, and so by that, just translating that from English to kind of probability, the increment WT plus h minus t would be the same as any increment of length h, and in particular this one. This is the increment from from 0 to time h. The elapsed time from 0 to h is just h, and so this is telling us exactly what this what the stationarity condition asks us for. An increment during which a time h has elapsed has the same distribution regardless of where that increment is placed. Here that increment is placed at time 0, here the increment is placed at time t. This should also remind you of the homogeneous property. So the Brownian motion is, it's called a homogeneous Markup process. We're about to see that the Markup property is also satisfied. And here's how you would, for example, compute this probability. So, you can compute the probability of the increment by using the stationarity to rewrite it as so. And then, we already know how to deal with this. This is just the integral of the density. This is our psi t x over the set A. This is the domain that the question is asking for. This is what we're asking for, the probability of the Brownian motion to be in set A. And so, the last thing to conclude is, kind of with why would this process be Markov? And, again, like the independent increments property that was inherited. Oh, and maybe I didn't actually explain how the stationarity came about. So both, all of the items here, the independence of increments, the stationarity of the increment, and the Markup property, they all are inherited from this interpolated scaled random walk that's approximating our Brownian motion. So we already discussed why two increments would be independent, because these xj's are separated in between these increments, at least for a small enough delta x and delta t. In the stationarity part, well, if you're taking some increment, let's say this one, or maybe let's look at this one, and we're shifting it. That's what we're doing when we're moving t here. We're keeping the length of the increment, let's say v minus u is equal to h. When we're talking about stationarity of the increment, we're moving the t in this definition and keeping the h fixed. So I'm just kind of moving this increment. And so why would that still have the same exact distribution as the one placed here? The increment placed here is that corresponds to this probability, and the increment placed here perhaps corresponds to this probability. Why are they the same? It's because these xj's are identically distributed. So we use their independence to find the independence of increments. We use their identically distributed property to argue for stationarity. And finally, you should be able to do the same thing for the Markup property. The probability that we find the Brownian motion in set A, given that we've observed the whole path of the Brownian motion up to time s, and here I'm again assuming s is less than t, should equal this probability. Specifically, you only need to know the where the Brownian motion was at time s to know that to be able to compute the distribution that it has at time t. So again, this is inherited from the Markup property that this would have. We showed right in the beginning that the discrete time random walk from which this process was derived had the Markup property, and the same exact thing happens here. So maybe this is where I can pick up from at the next lecture and look at we'll look at a number of other properties of the Brownian motion, including the martingale property. So for now, I think this kind of wraps up this lecture. Maybe the last thing I'll say here is that you may find it curious that the Poisson process has a definition that looks almost identical to the Brownian motion, with the exception of the distribution, but it's sort of you may find it kind of a curious thing, and the answer lies in the fact that you can actually design a random walk to kind of a process n delta that, when delta t and delta x go to 0, will actually lead to a Poisson process. But there it's the Markov chain that's derived is a little bit different, and if you're interested, we can talk about it in office hours. But that's just something that I want to draw your attention to for now.